Hello and welcome to these video lectures on software engineering for students. I am Abu Bakr Abid, a private tutor of 3 years and an IT professional. I've had a lot of exposure to software engineering in the past and have also had exposure to other aspects of the IT sector. I have designed these lectures in order to help you learn a little bit more about the principles of software engineering and hopefully to help you in your studies. The principles that have been discussed throughout the course of these lectures can be applied to both undergraduate and postgraduate study. However, please note that the content is not completely universal, and you should refer to your course module information to find out more. The prerequisites for understanding these lectures are that you have some understanding of the programming languages which are available nowadays, as well as some basic experience of some basic application development of a few hundred lines. That would be enough. The organization of these lectures will be as follows. First, we will cover the preliminaries, i.e. the background information that you will have to understand in order to go on to the following sections. The second lecture will be regarding the design element, so basic understanding of the design principles. The third section will go into the programming languages that can be used throughout the course of any project that is being built. Next, we will speak about the verification and testing processes that can be used. We will then speak about the process models such as the waterfall, the iterative, and the RUP models. Before the concluding lecture, we will speak about the project management aspect and how aspects of your project can be more effectively managed. It can be helpful to identify the categories of software which can be used. The first of these is games. Obviously, we are all accustomed to online games, Xbox, PS3, PS4, etc., etc. Secondly, there are information systems. Now, these can be large-scale applications which are used to store a lot of information, for example, a hotel reservation system. Thirdly, we can have real-time systems that have to be able to act quickly to the data that is being inputted, for example, the controlling of a power station. Next, we can have embedded systems. Now, these can be smaller roles within the computer itself, but they are part of a larger overall system, for example, a telephone exchange. We can also have office software, so we're all accustomed to the office suites such as Word, Excel, and PowerPoint. And lastly, we can have scientific software. Now, this can be software that is used for calculations, modeling, and predictions, for example, weather forecasting. Software can come in many forms. It can be off the shelf, for example, the Microsoft suites, or it can be something that's a bit more open source. All these types of software fall within the remit of software engineering. Information systems have a slightly different history, and generally they have slightly different techniques as well for their development. Often the nature of the data of information systems is used to dictate the structure of the software, so that analysis of the data to software development is outside the scope of these lectures. Constructing the software can also be a challenge, essentially because of the complexity of the software itself. The perceived problems that many people have said about the development of software is that, firstly, it's quite difficult to come into the expectations of the users and to obviously meet all their requirements. Secondly, it's quite hard to have a very low cost of production, and sometimes it's very expensive to build large-scale applications. Thirdly, it is quite difficult to get high performance out of applications due to the available architecture at the moment. Nowadays, portability is a very big issue, and sometimes it can be hard to integrate this into a project. High reliability is another aspect which is not as in-depth as the others, however, does need certain considerations. And going back to the first principle of meeting all the user's needs, it is quite difficult sometimes to deliver the project on time due to various problems which occur during the development process. Each goal is considered to be a problem because of the fact that software engineering is generally unsuccessful at reaching them. We will, during the course of these lectures, take a look at these goals in turn. And then later on we will try to combine them and try to come to a conclusion on the matters. Of the users or the client. So it may seem obvious to say, therefore, that software project must be helpful to the users. In order to develop software which is going to benefit everyone, then the development team have to take some care in doing this. And this step is often called requirement gathering or requirement analysis. So the first point that we must look at is how effective is a large-scale project. And it seems to be that a large majority is actually delivered on time or is delivered to some extent, regardless of the time aspect, but it's not used properly. And we need to understand, why is this the case? Another large percentage of this is taken up by, stuff that is paid for but not delivered. Again, this is another aspect of software engineering which has to be looked at a little bit in depth and see, why is software not being actually delivered to the clients. Another big aspect, which personally I have seen a lot of in experience, is that clients often change their requirements halfway through, which means that it has to be abandoned and started again, and this causes a little bit of confusion for the development team, and certainly me as an engineer. It's not the best thing to happen to you. Let's just put it that way. So it seems that a large proportion of the systems do not meet the needs of the end user, and therefore are not either taken advantage of or supplied. Let's have a look at this a bit more in depth, but let's first go into the cost element of this. So an example of cost, first of all, let's get some idea of the scale of the software costs in the world. In America at the moment, it is estimated that $500 billion is spent each year on the production of software. This amounts to just 1% of the gross national product. The estimated figure for the world is 1,000 billion being spent each year on software production. These figures are set to rise by about 15% per annum. The operating system that IBM developed for one of its major range of computers, called OS 360, is estimated to have cost just 200 million. In the USA, the software costs of manned space program were about $1 billion between 1960 and 1970. These examples obviously indicate that the amount spent on software is a significant proportion, and it is becoming industrialized. The cost of software is determined largely by the productivity of the programmers and the salaries that they are paid. So, perhaps surprisingly, the productivity of the average programmer is only about 10 to 20 programming languages or statements per day. To the lay person, the productivity of 20 lines of code per day seem disgraceful or insignificant. However, this is an average figure and it should be qualified in two ways. First, enormous differences exist between individual programmers. For example, I may not be able to code as quickly as a person who's been in the industry for 10 years. Likewise, someone else may not be able to code a certain language better than me because I've been doing it for a very long amount of time. Also, this apparently poor performance does not just reflect the time taken to carry out the coding, but it also indicates the time that is actually required to clarify the problems in the specification, the software design, the coding, the testing, and the documentation of the whole project. Therefore, the software engineer is involved in many more tasks than just coding. It is often a very common myth that a programmer is just going to be doing coding. Actually, in experience, I find it's a lot more. Speaking to clients, getting all the relevant information, clarifying information, going back, changing things, testing things, etc., etc. And this takes up a lot of time. However, what is interesting is that the figures I've just mentioned for the productivity is independent of the programming language used. So it is similar whether you have a low level programmer or a high level programmer. It is therefore more difficult to initially show the attributes and the level of the productivity to laziness ratio, if you want to call it that. So it's overall quite difficult to predict the costs and how long a software project is going to take. It's not uncommon to actually underestimate the required effort by 50%, and hence the cost and the delivery date are also affected. Obviously, if I was to now predict that a program is going to take me 6 weeks to build, it actually takes me 8 weeks to build, it's going to have an effect on the cost and the delivery time, because a lot more man hours are going into this. The impact of personal computers has perhaps had the greatest influence on popular perceptions of software costs, and with the advent of personal computing, it's somewhat more difficult. Many people buy a personal computer for their home and so come to realize very clearly that the costs are basically a CD or a stereo, or a bit of software for their application. However, if you buy a PC for $1,000, for example, you don't expect to pay $10,000 for the software, which is what it would cost if you hired a programmer to write it for you. So, of course, software for a PC either comes free or is priced at about the correct amount. For example, now Windows 8 is available for £80 in the UK, I think. I'm not 100% sure on that. So it can be hard to comprehend that something that you pay £80 for example, has actually cost $1 million to develop. Of this is Visual Basic and Microsoft Access, which are available very easily. These tools enable certain types of programs to be constructed very easily, and even people who are not programmers can actually learn to build fairly complex applications from these. So the perception is created that, it's quite easy to program. And indeed, programmers may no longer be necessary if applications grow. Certainly, the development of Office 365, SharePoint, and now Access apps has enabled companies to develop their own applications from Access databases, which means that more people are going to turn towards these as they may already have an Access database in-house, and can very quickly and easily have it on the cloud. Cloud computing is not something I'm going to go too in depth on in the course of these lectures. However, it will come up every now and then. The truth, though, is of course that some software is very simple and easy to write, and most commercial software is large and extremely complex. And it is where these come into play that we are now going to need the programmers and the principles of software engineering. The sophistication of today's software has far outstripped the past. For example, complex graphical user interfaces are now very essential in a lot of systems, and they are commonly implemented on the web, cloud computing, as I mentioned. And the sheer size of projects has mushroomed. People and organizations expect ever more facilities from computers. Arguably, however, as hardware becomes available to make previously impractical software feasible, software costs are only going to continue to escalate. So, going back to the cost element of things, how is the cost made up is another aspect which we need to look at. Surprisingly, half of the cost of developing a software is only the testing element, and coding is a mere sixth. A third of the whole cost is actually analysis and design. People sometimes think that coding is the biggest element. Well, actually it's not, because gathering the information takes a lot of time, and analyzing the information to create the right design and mix of elements is in itself a project. Coding actually takes the least amount of time because of the fact that you have to just code. You have all the designs ready for you. You just have to turn those into an application that works. If mistakes are major problems, when are they made? So we can see that the number of errors at various stages of the project are shown on the screen at the moment. The longer the fault remains undiscovered, the more fault costs to fix it, is the rule generally, because of the fact that if this project has been going on and has been implemented now, it is being used. If it is being used, then there is a certain amount of data being stored. This data being stored is building up the size of the application, therefore could be causing errors somewhere else as well, and you just haven't found those errors yet. A design flaw made early in the project may not be actually found until very later on in the testing, or even after it's been implemented, because this has always been a headache for software production. For example, surveys have consistently shown that this is the worst problem faced by any project manager, and certainly I have found this as well. The problem is related to the difficulty of predicting how long it is going to take to develop something. If you do not know how long it is going to take, you cannot hope to meet any deadline. It is common experience for a project to run late and over the budget, This often leads to a very unhappy client and causing a little bit of problem among the software development team. Evidence suggests that around 60% of projects exceed their initial budgets, and around 50% are completed late. Whatever the exact figures, meeting deadlines is clearly a problem. Back in the late 1980s, I think, IBM launched, obviously, OS 360, as I discussed earlier, for its prime new range of computers for basically 1 year late. The computers themselves were basically sitting around in the warehouses, and in that time, Microsoft managed to obviously bring out their systems a little bit ahead of IBM. But again, this is down to speculation as to what happened behind the scenes. We do not have all the facts in front of us. So next we're going to speak about software performance, and this is sometimes called efficiency. This terminology dates from the days where the cost and speed of hardware meant that every effort was made to use hardware, primarily the memory and the processor, as carefully as possible. More recently, however, there have been changes due to the increasing speed of computers and the fall in the cost, and nowadays there is much more emphasis on meeting people's requirements, and consequently we will not spend much time on performance throughout the course of these lectures. However, despite this, the performance cannot be completely ignored. Often it is concerned with interactive systems which have a reasonably short time, and a control signal output, for example. Games are a very major element of this, because games have to be quite efficient and fast in their experience of using them. Portability, as I mentioned earlier, the dreams of portability, well, they have always been able to transfer one software from computer to another device with minimum expenditure, minimum effort as well. With the advent of the high-level languages that are available now, and the establishment of international standards which exist, and interoperability as well, the prospects look bright for the future. And certainly this can be said for Apple, who have successfully managed to launch handover of certain applications such as Pages, Numbers, Keynote, Safari, Messages, and so on, where you may be working on your laptop and you can pick up straight away from your iPhone, or vice versa, exactly where you left off. The reality is that obviously the market is going to basically determine the situation. A supplier seeks to attract a customer by offering something which is above and beyond their expectations. Typically, these may lessen the work for software development. An example is an exotic file access method. Once the user has brought the system, he or she is locked into using these special features and facilities of the system, and is reliant on that company or the companies that are going to make the software for that specific operating system or hardware to be compatible. The contradiction is, of course, that each and every user is tied to a particular supplier, and only switch can be made by investing a very large amount. Only large users like corporate bodies and government agencies can really adopt standards of changing every now and then. Obviously, you don't want to be investing constantly. Maintenance is another aspect which we will discuss later on, but just to give you a quick roundup of this, maintenance is a term for the effort that is put into the software to ensure it is operating in a good way and consistently. Two types of maintenance exist. You have remedial maintenance, which is the time spent on correcting the faults and the bugs, and adaptive maintenance, which is going to be modifying the software because of the user's needs, which have changed or that have become a little bit more complex than were initially expected. In the next section of these lectures, we will be discussing the tasks of software development, so please do join us again for that.